With all that we have learned so far, we are now in a position to derive some basic relationships which govern the movement of objects in a straight line. Now, in order to keep things simple, we will make one crucial assumption that all of these objects are under uniformly accelerated motion, which means that for any given interval of time, the rate of change of velocity will remain uniform. Let's look at these equations. The first equation says that v is equal to u plus at, where v is the final speed or velocity of the object at the end of the interval of measurement. U is the initial velocity or speed of the object at the beginning of the interval of measurement. A is the uniform acceleration on the object in this time, and t is the interval of time over which the observation was made. The second one is s is equal to ut plus half at squared, where s is the displacement of the object in the given time interval t, and all the other figures have the usual meaning. And the last relationship is v square minus u square is equal to 2as, where all the symbols have their usual meanings. Now let us look at the first equation. V is equal to u plus at. Let us see how we can derive it using a graph. We construct a graph showing the change of velocity of the object with respect to time. Let us consider the quadrilateral AOCB in this velocity time graph. The various sides of this quadrilateral correspond to various pieces of information that we require. For example, at the bottom we have the segment OC. Since it is on the time axis, the length of segment OC represents the time interval over which the object is in motion and under observation. On the other hand, the two parallel sides of this quadrilateral, which are given by the segments AO and BC, give us the various speeds of this object at the beginning and at the end of this observation. They also correspond to the initial and final velocities of the object at the beginning of the interval and the end of the interval. If we look at this graph, it is easy to see that one side is significantly bigger than the other, which means that the final velocity of the object is greater than the initial velocity. In other words, v is greater than u. Since the length AO represents u and the length BC represents v, we need to find a way by which we can link these quantities using an equation. To do this, what we will do is draw a line AD which is parallel to OC. So now in this case, we have a new line segment BD, which is equal to the difference in the final and initial velocities or speeds of this object. Putting this all together, we know that the change in velocity over a given amount of time gives us acceleration, or in other words, v minus u divided by t gives us acceleration, or v minus u is equal to at. Using these relationships, we can see that the lengths of these line segments correspond to the change in the velocity of the object from the beginning to the end of the interval. Since v minus u is equal to at, it follows that v is equal to u plus at. We shall now derive the position-time relationship for uniformly accelerated motion. Coming back to the quadrilateral AOCB, we can make the observation that the area under this graph or the area of this quadrilateral will correspond to the total displacement undergone by the object in the time interval of consideration. As in the previous case, the line segment OC, which forms the base of this quadrilateral, is the time interval over which the observation is made. We draw a line AD, which is parallel to OC, which splits the segment BC into two parts. We observe that we can look at this quadrilateral as the combination of a triangle and a rectangle, and we can compute the areas of the triangle and the rectangle separately. Looking at the rectangle at the bottom, we observe that the area of this rectangle corresponds to the length, which is given by the segment OC or AD, multiplied by the height of the rectangle, which is given by the segment AO. As we did previously, AO corresponds to U, that is the initial velocity at the beginning of the measurement, while OC corresponds to the time interval t over which the observation is made. So the area of this rectangle is given as the multiplication of the sides, which is equal to U multiplied by t. Looking at the triangle, we observe that the base of this triangle, which is AD, is parallel and equal to OC. So AD is also equal to t. We also observe that the height of this triangle given by the segment BD is actually the change in velocity, which is given as V minus U, and that gives us AT. So the total area covered by this quadrilateral is the area of the rectangle plus the area of the triangle. The area of the triangle is given by half multiplied by base multiplied by height. Substituting all the values that we have discussed so far, we get displacement, which is S, is equal to ut plus half at squared. We are now in a position to see the relationship between displacement and velocity, or position and velocity, for a uniformly accelerated object. Looking again at the figure that we have used previously, we notice that it is a trapezium. Now, if you rack your heads to what you did in measurement a few years back, you will see that the area of a trapezium is given by half multiplied with the sum of the parallel sides multiplied by the perpendicular side between them. Looking at the graph, we can see that the sides AO and BC are parallel to each other, and the side OC is perpendicular to both of them. So we get the relationship half multiplied by AO plus BC multiplied by OC, where AO corresponds to U, BC corresponds to V, and OC corresponds to t, the time interval over which the observation takes place. Looking at the first equation of motion, which says that V is equal to U plus AT, we can also see that t would be equal to V minus U divided by A. So substituting the value of OC in the previous equation, we come to the result V square minus U square is equal to 2AS. Let us remember that in all of these cases, acceleration remains constant with respect to time.